Hey guys, today we are looking at our notes for 8.3, which is now all about geometric sequences and series. As we talked about yesterday with arithmetic sequences and series, we can write their equation using a specific formula. We should be able to write terms of our sequence, write our equation of the sequence given some different information, and then just like yesterday, we've got a little shortcut for finding the sum of a finite series that is now geometric. So, first and foremost, a geometric sequence. We know that we have a common multiplier or divider going from one step to the next. Technically, the way we define it is there is a ratio from any term to the previous term is constant, meaning there's a constant ratio called the common ratio, or R value, our multiplier, in our equation takes me from one to the next. Now, for us, most of the time, it is easier for us to find whatever that constant multiplication or division is. Especially what we find, like what we have to multiply by to get from one to the next, is far easier for us to do than to go through and actually establish what those ratios are, but that is an option for us as well. In our formula, so this is our formula for a geometric sequence, a sub 1, that's always the first term in my sequence, and then r is your common ratio, which is also the same thing as your multiplier. And then a sub n is still a term, n is still the term number, the position number of that sequence. But again, the two things that we will replace in our equation would be a sub 1, which is the first term, and then r, which is the common ratio or the multiplier. So in box 1 here, we're just determining if the sequence that we're given is geometric, meaning is there a constant multiplication or division that gets me from one to the next in my sequence. So there's a couple different ways that you can check for this. You could, if it's obvious to you what multiplication or division takes you from one to the next, you can go ahead and do that. So like in number 1, it's pretty easy for most of us to see that that 6 times 2 gets me 12. But because times 2 does not work to get me from 12 to 20, that pattern is not consistent, meaning there's not a constant multiplication that takes me from one to the next in my sequence. So that leads me to believe, or it leads me to conclude, that this is not geometric. It would have to be a constant a constant multiplication or division getting me from one to the next in order to be geometric. Now with number 2, it might be clear to you what my pattern is for multiplication or division. Maybe you see, especially towards the end here, that 16 divided by 4 is 4, and then you check to see, all right, well, 64 divided by 4 is also 16, 256 divided by 4 is also 64, right? So dividing by 4 each step of the way does fit in my pattern, which means if I was asked to identify it, my r, which is always that multiplier, would have to be 1/4, since it looks like dividing by 4. Either way we do that, we should conclude that this is geometric. Now, the other thing that you can do, if it's not clear to you, like sometimes it's not just a straightforward multiplication or division by a whole number, the other thing that you can do to check for your ratios, to figure out what that r value is, you can take a term and divide it by the previous term. So if I wanted to do this using another method, I could check 64 over 256, 16 over 64, 4 over 16. All of those are my term divided by the previous term. And if we used our calculator or our big brain, we would realize that all 3 of those different ratios reduce to 1/4, which means not only is it consistent, but that is my r value. R is 1/4. So either way, if it's obvious to you and you can identify what those multipliers or divisors are, that's awesome. Go ahead and do it that way. But if you're stuck on what it is, you can always do it that other way as well with the ratios. Term divided by previous term. Just like it says in the instructions up top. The ratio of any term to the previous term, meaning any term divided by the previous term, is constant. All right, box 2. For this one, we are writing the rule for the nth term of the sequence and then finding a sub 8. So finding the 8th term of the sequence after we've identified what the equation is. So in our equation, again, the two things that we need our a sub 1 value, our starting value, which that's easy. It's right here. Right, the very first term is a sub 1, is positive 5. And then my r is my multiplier. So how can I get from 5 to 15? Well, that's just times 3. It's always a good idea to check to make sure it does work consistently, which 15 times 3 is 45. Use your calculator. 45 times 3 is 135. So my equation for number 3 should be a sub n equals my a sub 1 value, which is 5, times 3 to the n minus 1. So I'm just using that formula from over there in box 1. A sub n equals a sub 1 times r to the n minus 1 power. To find the 8th term, we simply plug in 8 for my n value. So I'm going to make this a little bit bigger. To find a sub 8, I'm going to just do 5 times 3 to the 8 minus 1 power, which is 5 times 3 to the 7th power. And I can use my calculator to identify or calculate that this comes out to 10,935. Let's box this in just because they do ask us for both of those two things. So there's my equation, and there is the 8th term. All right, looking at number 4. Number 4, again, lead term is my a sub 1 value. Now to get from one to the next in this one is a little bit confusing because I see my sign is alternating, so I know I'm going to have to be a negative number. And here, since I'm looking for r, I want to try and figure out what I'm multiplying by. So I know I have to multiply by a negative, and it looks like we're dividing by 2, right? Because 88 divided by 2 is 44, 44 divided by 2 is 1/2, is 22, 22 divided by 2 is 11. So since we're dividing by 2, that's the same thing as multiplying by a half. And since our sign is alternating, we want a negative 1/2. Because negative 44 times a negative 1/2 is positive 22. Positive 22 times a negative 1/2 is negative 11, so on and so forth. So our equation, a sub n, should be 88, that's our a sub 1 value, negative 1/2 to the n minus 1. And that is our equation of that sequence. That's our rule for the nth term of the sequence. Now again, finding my 8th term, a sub 8, I'm going to plug in 8 everywhere I have n, so negative 1/2 to the 8 minus 1 power, which is 88 times negative 1/2 to the 7th. So on your calculator, you would do negative 1/8 to the 7th power times 88, which, depending on how you want to do this, if you're going to use your calculator, it'll probably spit out negative 0.6875. If you do it the old-fashioned way, with negative 1/2 to the 7th power being negative 1/2 to the 7th, and then multiplying by 88, you end up with negative 11/16. Either of those two, totally fine, but that should be my solution for number 4. All right, over here to box number 3. Box number 3, very similar to box 3 yesterday. We are now trying to write our equation of our sequence, our rule for the sequence, given a particular, some random term in my sequence, and knowing what my pattern is. So in this case, for number 5, I'm given that my 4th term is 12, and that my common ratio, my multiplier, is 2. So they want us to first write the rule for the sequence, and then tell us what the first 6 terms of the sequence are. So just as a quick refresher, so we have it handy here, here is our equation for my geometric sequence. So the things that I'm given my r value, that goes right there. I'm given my a sub n value, so I'm given that the 4th term is 12. So what that tells me is that when I plugged in 4 for my n value, I got a 12 for my a sub n. So I know everything in here except for my a sub 1 term. I don't know my first term, my starting term. So I'm going to go ahead and just do that substitution. If I do that, I have 12 equals a sub 1 times 2 to the 4 minus 1 power. And now I can go through and solve for a sub 1. 12 equals a sub 1 times 2 cubed, which 2 cubed is 8. Oops, that's supposed to be an equals a sub 1. So I divide by 8 on both sides. And a sub 1 equals 12 over 8, which reduces to 3 over 2, or 1.5. So now that I have that, I can put that back together with my equation. I can write my rule. I'm going to switch to red here. So a sub n equals, we now know that my starting value is 1.5, 3 over 2. My r value was given to me, to positive 2, to the n minus 1 power. There's my regular equation. And now they want us to write the first 6 terms of the sequence. Now we can do this strategically. We don't have to plug in 1 through 6 in my equation for n. I know that the first term, a sub 1, is 1.5, right? 1.5. And I also know that my r value, my pattern to get from one to the next, is multiplying by 2. So instead of having to plug them all in, 1.5 times 2 is 3, times 2 is 6, times 2 is 12, times 2 is 24, times 2 is 48, and that should be 1, 2, 3, 4, 5, 6 terms. There we go. There's the first 6 terms of my sequence. All right, last but not least, box 4. So box 4, we're now going to a geometric series. So now we're finding a summation, or we're performing a summation, we're finding a sum. In what we're looking at today, we're still looking at a finite series, meaning there's a set number of terms, and now it's geometric. So we have to recognize that a sub 1 times r to the n minus 1 power as my index, and then from here, once we recognize that, all of this information in my formula is just from that series. So in here, my a sub 1 is still that first term. My r value is still my common ratio, or your multiplier, depending on how you want to look at it. And then this n, right up there, that's the upper limit. So that's how many of those different terms we're adding together, or sorry, multiplying together. So let's go ahead and just jump into finding the sum for number 6. For number 6, we are asked to find the sum of this series that goes from k equals 1 to positive 10. So in our equation, remember that our front number here is our a sub 1, and this inside my parenthesis, the base of my exponential term, is my common ratio, my r value. And then right here, that's my n. So again, just labeling everything. This is a sub 1, this is my r, this is my n. And those are the 3 things that I need in my equation. Everything else is just ones and that. So going over here to my equation, my formula, the sum of the first 10 numbers in this series is equal to my a sub 1, which is 4, times 1 minus my r value of 3 to the n power, my upper limit, my 10, all over 1 minus my r value, which again is just 3. So that's my formula. I'm just plugging in a sub 1, r, and n into my equation, into my formula. From here, it's just evaluating. So now it's just getting your calculator, evaluating your numbers. Make sure you just follow order of operations. So I should be working inside out. So 4 times 1 minus 3 to the 10th is 59,049, all over -2, because that's 1 minus 3. So we've got 4 times -59,048 over -2. So depending on how you want to think through this, let's just say my negatives cancel. This 4 and this 2 reduce to a 2. So 59,048 times 2 should give me a total sum for the first 10 numbers in the series of 118,096. That is the sum of the first 10 numbers, 10 terms of that series. All right, so homework is down there at the bottom. I'll scroll up a little bit so it's easier to see for some of us, especially if you're in person right now and you're trying to watch that over top of the pile of crap that's on my table. There it's easier to see. Page 430 to 431, 6 through 28, and 48 to 52 evens. As always, if you have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. Otherwise, have a fantastic day. We'll see you soon.